In this video, I will explain the meaning of the mathematical quantifiers, which are these two symbols. This symbol, an upside down A, means for all or for every. And this symbol, a backwards E, means there exists or there is. And a quick note, in mathematics, whenever we say there exists or there is, we always mean at least one. We don't mean exactly one. This is in all contexts. For example, if I say an equation has a solution, it means has at least one solution. If you want to say something different, say so explicitly. Let's look at some examples of these quantifiers in statements. The first statement says, for every real number x, x squared is greater than or equal than 0. Or in other words, every real number satisfies that the square is greater than or equal to 0. And we know that that is true. That's a property of squares. The second says that for every integer x, x is greater than pi. And that is false. Some integers are greater than pi, some integers are smaller than pi. For example, 1 is smaller, and that's enough to say that this statement is false. Okay, next, let's look at some examples of statements with there exist. The first statement says there exists a real number x, x squared equals 5. And I'm going to pause here for a moment. This statement reads really weird. As an English sentence, it's not quite grammatically correct. We kind of need a connector in between. We cannot just say it as I read it. And the connector we normally use in math here is such that. Now, this didn't add anything mathematically. It didn't change the meaning. It just made it make sense grammatically. And I think it makes the sentence easier to read. You don't have to write it. Logicians never write it. They write a comma. But I think it helps making the sentence easier to read. Okay, now let's look at the meaning. There exists a real number such that x squared equals 5. And yes, there is one such real number x. This is true. In fact, there are two, but one is enough. So for example, we can say that x equals minus root 5. That's a number that satisfies that. Now, the second statement says there exists a real number x such that x squared equals minus 1. And that is false. No real number satisfies that. To finish, I want to compare these two statements with something else. If I simply write x squared equals 5 and nothing else, is this true or false? Well, I want to say neither. The answer is that this is meaningless. In logic, we could say that this is not statement, it's a predicate, but don't worry about that. It just means that as it stands with nothing else, this is neither true nor false. Unless we have previously agreed on the meaning of x, for example, perhaps we fix x to be a certain value, this means nothing. Because what are we saying? Are we saying this about all values of x somewhere, or that there is a specific value of x in some set? Or are we saying pick your favorite value of x satisfies that? We need context. So if you're ever tempted to begin your definition or your theorem or your proof with a statement like this without having first fixed the value of x or explaining what you mean by that, don't do that, because that will be neither true nor false, meaningless, which is much worse. In the next few videos, I will explore the use of quantifiers in more complex contexts.